How's everyone doing today? Great. So we are still missing just a few people, so we'll wait until 1:03 to start the lecture. Before that, I've changed into a new background. So to continue our world tour. So this is perhaps an easy one for people to guess. Can anyone? Yes. Awesome. Alex said it's Switzerland, but where specifically in Switzerland? Do anyone know? Yeah, this very prototypical Alpine like Swiss Alps landscape is typical of Switzerland. So this is a little town called Interlaken in Switzerland. And literally this means in between two lakes, in between the lakes, Interlaken. Laken is a like plural form of lakes. And behind the scene, besides the two lakes that are sandwiched in this town in between, behind the scene that's a Jungfrau mountain, and that means that the young I guess young girl, young lady mountain. So that's one of the very nice tourist town in Switzerland. Even within Switzerland, this is considered one of the winter's paradise for people to hang out, and also summer's paradise for hiking and all the other activities. So the interesting thing about Interlaken is that it features a lot of the train tracks that actually take you from the town all the way to the mountaintop that's above the sea level by I think 3,000 or 4,000 meters up in the air. So that's a pretty fun ride to take, especially if you have young kids. But make sure that you bring oxygen or you stay really fit, because otherwise you might have the alpine effect that makes you dizzy when you are on top, even if you just go up by train. Okay, so looks like we have everyone. Let's start the lecture. So today is the 16th lecture of convex optimization. We're going to be talking about algorithms for online convex optimization. So far, we've talked about several algorithms. At the first lecture, we talked about multiplicative weights algorithm that applies to a simple setting of learning with expert advice. And then we talk about a generic algorithm, online gradient descent. In the last lecture, we talk about an extension of online gradient descent that allows us to get, in some sense, better constants in various cases. So we can generalize online gradient descent from the Euclidean geometry to other geometry with a given regularization function R. So in the last lecture, the algorithm that allows us to do that is to follow the regularized leader. Okay, suppose we have a regularization function, a convex function R of x, and follows the regularized leader algorithm simply updates the weights, updates the parameters that you're optimizing over using a regularized objective by finding x that minimizes this linear objective function using all the information that's available so far from the full information setting. So notice that in the full information setting, after playing each round, you receive a feedback in the form of the gradients, gradient of ft at your chosen location. And the difference in follows a regularized leader is that now you have an additional regularization term here. And depending on what the regularization term nuclei, and then you can get a slightly different regret bound. So we've proven that the regret is smaller than dr and gr and square root of 2t. Okay, so this recovers the regret bound of online gradient descent when R is chosen to be the square Euclidean norm. But suppose R is chosen to be something else, then you can recover other type of dependence on the dimensionality of the problem. Okay, so the definition of this dr is a generalized diameter or with a norm that's measured using R. That's defined as for any xy in, I guess this is in the constraint set K, takes the difference between the convex function Rx and Ry, and then you take square root. So that's how you define the diameter. So this is a strict generalization of the Euclidean distance. And GR, on the other hand, is the upper bound of the gradient that you observe, but measured in this norm called, that's specific to every time point for any t, and this is a dual norm of this t norm. Okay, so recall that our definition of this t norm is equal to of the Hessian of this t norm, we're just using this as an abbreviate of the norm that's evaluated of at location z in between x and xt plus 1. So this z is something like on the line segment, but without specifying what exactly it is. Therefore, the dual norm of this Hilbert space norm would be the norm, the quadratic form style norm that's defined on the inverse of the Hessian matrix of this R. Okay, so this is a pretty abstract result that allows us to choose an arbitrary R, and in the proof of this result, we've done like one thing that I think is worthwhile talking about again, that wasn't too clear when I was presenting that on our Monday lecture. So so here's what it is. So when we prove the regret bound, we bounded the difference between between these two. In some sense, we bounded the difference between two linear functions rather than the original convex function that we're dealing with. Okay, so what wasn't clear is that why does it solve this original problem that gives rise to this theorem with the regret bound? That recall that the regret should be defined to be should be defined should be an upper bound that depends on the sum of ft xt t from 1 to t minus t to t ft x star, right? For a sequence of adversaries chosen at t f1 to ft. Okay, so what I didn't say clearly is that why is this okay? Why is it okay to bound the differences in the linear terms while ultimately we want the regret bound of the convex term, convex functions? Okay, so I guess the point is really to apply the definition of convexity. So by the first order definition of convexity, so you can clearly write ft xt minus ft of any u, and then you can bound it from above by the linearization of it. So this is simply, and that gives us what we proved to have this regret bound on the right hand side. Okay, so how do we interpret this? So again, this is simply follows from convex FT. How do we make sense of this? So what this is essentially saying that when we're not making any additional assumptions about this convex function f, it suffices to bound the sequences of their linearizations, and we can use the regret bound on the linearized objective function to upper bound the regrets of the original function for any convex function f. And to say that more explicitly, this is saying that the linear functions are the most non-convex functions among the family of convex functions. Therefore, if you can solve that, you've already solved the hardest convex. It's like the marginally convex case. And if you can solve the linear case, then essentially you can use it to solve any convex case. And then like in order to substantiate the value of the follow the regularized leader for a bit, we considered the special case when this R of x is equal to x transpose log x. So this is the sum of I from 1 to n xi log of xi. So this is the negative entropy. Okay, and the domain is when x is a probability simplex. We adopted the notation of this delta of n. This is for all x satisfying x larger than 0, and the sum of x is equal to 1. And for this specific R of x, we've worked out that this GR is equal to 1, which allows us to plug this in. So it remains to work out DR. So I left this as an exercise to show that under this setting, this DR is smaller than log n, which gives rise to the final bond that looks like order square root of t log n, which is an exponential improvement in terms of the number of experts that this supports, comparing to the ordinary to the standard online gradient descent method, which only gives us the square root of t times the square root of n. Okay, and the corresponding algorithm, suppose you use this R of x, recovers the hedge algorithm, or also known as exponentiated gradient, which enjoys this type of regret bound from our first lecture on online convex optimization. Okay, so I encourage you to work out this upper bound of log n for DR. It's not very difficult. So you can try to come up with like just add and subtract things to construct the KL divergence, and then everything becomes pretty straightforward, and then with a simple Holder's inequality. Okay, so there's one last thing I wanted to talk about the follow the regularized leader before we move on to talk about online Newton method. Is a different interpretation and a slightly different approach of how we would end up getting the final regret bound. So recall that in our analysis, we rely on a key lemma that deals with the bounding the regret of any algorithm, bounding the regret of the algorithm that we're analyzing using the regret of a fictitious algorithm for called the Beazer leader. So the key lemma, which says that the regret that we're trying to bound is smaller than the regret relative to Beazer leader. Again, it suffices to only talk about linear regret thanks to this equation. So Beazer leader again is an a non-realizable algorithm that you cannot run in practice, but it's useful for analytical purposes, that can see one step ahead into the future and then play the leader and play the empirical risk minimizer xt plus 1 at time xt. Okay, so this is measuring the regret against be the leader plus this additional term that depends on dr squared. Okay. So what this is saying is that suppose we can show that the changes from xt to xt plus 1 is not too significant, and the cumulative changes of this xt to xt plus 1 are bounded by some quantities that's sublinear, then we can make use of this fact to achieve low regret. So this is a stability approach. Stability approach of obtaining the regret bound, and we've provided a lot of intuition why stability is required, and an algorithm without stability can very easily fail and end up having a linear regret. Okay, so the key of the analysis of the regret on the follow the regularized leader was to carefully construct a bound of this quantity. So we used a very long argument to show that this term is smaller than 2 eta times the norm of the gradient at t measured in this dual norm that's specific to this regularization function r. Okay, and with this, that like very straightforwardly leads to the final regret bound. So today I wanted to talk about an alternative view of this problem, an alternative view of bounding this inner product of this key lemma, so that we can maybe have a bit more insight on what exactly this entropy regularization is doing. So this alternative view is from strong convexity. Okay, so so notice that we can simply use Holder's inequality to upper bound this inner product, and we can bound this by gradient t L infinity xt minus xt plus 1 norm. Right? We can just use a Holder decomposition of the 1 norm and infinity norm. And since we know that in the learning with expert device and also in the hedge algorithm, we're assuming that the loss or reward of each expert is bounded. Say let's without loss of generality, say it is bounded by 1. Then the linear function of this gradient is simply 1. Right? So this reduces to xt minus xt plus 1. Then more generally, you can replace this with an L infinity upper bound of the gradient. So this is a Lipschitz constant that's measured in terms of the L infinity norm. And I argue that for the entropy loss, we can more easily show that this term is smaller than eta times is smaller than eta, therefore the sum of these two, xt minus xt plus 1, would be smaller than eta times t. So notice that over here, ultimately, once we add everything up, we'll end up getting this expression, eta times t. Okay, so the idea leverage upon the fact that the entropy regularization, so this R of x equal to x transpose log x, is actually strongly convex. This might be somewhat surprising. So this is actually strongly convex, but strongly convex with respect to a different different geometry in L1. Yeah, there's a question that I didn't see on the chat window. So Peng said that the log n is on the square root. So which one are you referring to? Oh yeah, that's right. I think you can bound this with order of square root of log n, which makes this in a square root. Okay, yeah, good catch. Um, so so this is a property that you're going to be proving in homework 4. So so there's a homework question where you are supposed to prove that this entropy regularization is strongly convex in L1 for all x in the probability simplex. Okay, so using that fact, it actually becomes quite easy to establish a bound on xt plus 1 minus xt in terms of the one norm. Okay, so we want to bound this. So well, let's apply the let's define this function f. Function f to be, say, the sum of the quantities so far, all the gradient, inner product with x, plus r of x. Eta is here. So notice that since this one is, I guess, one strongly convex in L. So since this one is one strongly convex in L1, then we can then the sum of these two functions remains strongly convex in L1 because one of the term is strongly convex, and adding additional linear term doesn't really change the fact of the strong convexity. So we can apply the definition of strong convexity by decomposing this f at fxt and also decomposing this f at fxt plus 1. Right, so we can get t plus 1 larger than the linearized lower bound, but plus an additional quadratic vector. I guess that linearized at xt plus 1 minus xt plus half. Since this is one strongly convex in L1, so I can put 1 here, xt plus 1 minus xt square. 1. Okay, so this is by definition the strong convexity that's measured in one norm. Now let's also decompose this at xt plus 1 and then have the similar expression. Now this is xt minus xt plus 1. Notice that since yeah, and add xt plus 1 minus xt to one norm. So notice that we can simply just add these two things up, and then the leading term would get canceled out, right? So you have 0 larger than xt plus 1 minus xt gradient of f at xt minus the gradient of f at xt plus 1 plus xt plus 1 minus xt square one norm. When you move this to the other side, and then you can upper bound this with Holder's inequality, and then get xt plus 1 minus xt square one norm smaller than xt plus 1 minus xt one norm, and the L infinity norm of the two gradients. Okay, so notice that the L infinity norm of the gradient satisfies that it can be bounded by it can be bounded by eta, right? So you get basically you move this to the other side and cancel out with the square root of 2. Then you get then you end up getting xt plus 1 minus xt 1 norm smaller than eta, which recovers what we wanted to get in this alternative view. So that allows us more easily to construct an upper bound of this using the strong convexity property of the entropy regularization in L1. Okay, so let's start a new page. So in today's lecture, the motivating example of doing online Newton's method and further generalizing over the online gradient method and follow the regularized leader is the following example that we talked about in the first lecture called a universal portfolio problem. So think about that you are a trader and you are trying to grow your wealth in face of a uncertain and possibly adversarial stock market, and your decision, the decision that you have to make every day is how much each type of stock or each type of future or any kind of instrument that you wanted to hold. Okay, and that can be described by a decision variable xt in the probability simplex. Okay, so this measures your asset allocation in terms of the percentage of all your money and how much you wanted to invest in each stock. Okay, and then there's this relative price ratio that occur after you've made the decision every day. That's always non-negative. So this is the price ratio. So notice that RT, say for a particular stock I, is the ratio of the price it is today divided by the price of this stock yesterday, T minus 1 I. Okay, and this price of it, the previous day is when you have to base your decision xt upon. Okay, and I guess the total wealth based on this specification of time t plus 1 is equal to I guess the previous day's total wealth multiply with RT transpose of XT. Okay, so if this is the amount of money that you are investing according to this asset allocation, and then each asset would grow multiplicatively by the relative price ratio, and then it's straightforward to calculate that this is this number is how much you earned or how much you lose after this day of trading at time t, at day t. Okay, so if we just keep training this all together, say that there's an initial point when you have say $1, and then you keep investing it for capital T day. Then after capital T day, the total amount of money that you have would be T from 1 to T RT transpose XT. This is total wealth after T days. Okay, so we may like change it a little bit so that we recover something that we can use like online convex optimization for. So let's divide both sides by W1 and then take log. So because your decision is really independent to how much money you have each day. So log of Wt over W1. So this is equal to, so by doing log, we can convert the summation, we can convert the product into summation. So we get the sum of t from 1 to t log of Rt transpose xt. Okay, so all these log functions are concave functions since its support is non-negative. If we frame ourselves in the notion of online convex optimization, we think about minimizing cost rather than maximizing reward. So we define ft to be negative log of Rt transpose x. Okay, and this is equal to minus the sum of t from 1 to t, ft xt. Okay, and the corresponding regret in this problem is equal to sum of t from 1 to t, ft xt minus ft of any reference, any fixed reference u. So what does the low regret algorithm mean in the context of universal portfolio? What does it mean in terms of the growth of my wealth? Suppose I'm running this algorithm. So let me give you a few examples to motivate the problem more clearly. So notice that the regret is against any fixed u that can be chosen in the hindsight. So after everything is realized, right? So if you look back into the past and look at 10 years of the stock market, and then you look at say n stocks of your interest, and then you can contemplate. Suppose you started your investing in 2000, or suppose you started your investment even before that, and then you have run this algorithm, and then you are able to compete against the best fixed asset allocations. So in particular, you may choose u to be something that's one of the standard basis. Okay, you can choose any of the standard basis. So maybe like this one is Apple. Okay, maybe like this EI. Maybe this one is Tesla. Like maybe this one is NVIDIA. Okay, if you look back at it, and this regret is saying that the growth of your portfolio, your total wealth, like in a, I guess there's a logarithmic transformation, which is saying that so the growth rate of your chosen portfolio without all the knowledge that's available in the hindsight is going to match the best performance of any of these individual stock. But I argue that this can be even better than competing with any of the individual stocks. So in the sense that there are choices of you that in the general probability simplex that can lead to even better performance in any individual stock if you hold that individual stock from the very beginning. Okay, so I'll give you an example of that. So again, this is related to a homework question that you're supposed to work out. So let's consider the simplest case where there are just two, I guess, two stocks. So the two stocks have a RT that equals to say 2 half, 2 half, 2 half, and so on and so forth. And the second stock would be half, 2 half, 2 half, 2, and it goes on and on and on as t equals to 1, t equals to 2, t equals to t. Okay, so in this case, it's clear that if you keep holding just one stock, then you won't have any growth at all. So after t iterations, you're still like jumping around, like halving your total wealth, and then having a total wealth that's that's double. So your total wealth will be bounded within a constant factor, no matter what this t is. On the other hand, like suppose you consider this u to be 0.5, 0.5. Okay, suppose you just split your money and invest half of your money into each stock. So notice that you don't just do that once and let it go. Instead, you need to somehow rebalance every day. So in day one, you use half of your money to hold the stock A, and then the other half of your money to hold stock B. And in day two, after the stock A becomes double the price, and the stock B becomes half of its original price, then you rebalance yourself and buy more of stock B, and then by selling more of the stock A, so that you can control your ratio to be 0.5, 0.5, right? So this is an example of the so-called constant rebalancing strategy. So suppose we calculate what is the total gain that we will end up getting, suppose we adopt this strategy. So it's a pretty straightforward calculation. So WT is equal to W1 times the product of R from 1 to T, RT transpose U. And since U is taking the average of the two, so this becomes W1 times half times 2 plus half times 0.5 equals to the power of T is equals to W1 multiplied 1.25 to the power of T. So comparing to a single stock, this one, like one of the comparators in the class that may or may not be optimal actually have exponential growth at every time point. Okay, so being able to compete against the best constant rebalancing strategy is non-trivial, and that allows you to gain, say, potentially exponentially comparing to just holding any individual stock and competing against on a one stock. So how can all the algorithms that we've learned so far like solve this problem? What is the regret of, say, running OGD on this problem? What is the regret of running follow the regularized leader with entropic regularization on this problem? Since the argument is defined on the probability simplex, is something natural to try, right? So so we've already seen that if we use OGD, then the regret bound is G times D times square root of T. And both this G and D are measured in terms of the Euclidean norm, which gives a Euclidean norm of the gradient. So this is on the order of since the gradient, since G has bounded L infinity norm and D has bounded one norm, which implies a bounded two norm. So D is just one, right? Thanks to the probability simplex. But G is proportional to square root of n, because each individual coordinate can be one, and G is the sum of the square of that, and then you take the square root of the outside. So ultimately you get n times T regret. Follow the regularized leader with entropy regularization would improve the regret a little bit, and that so you end up getting a regret that's square root of T times log n. Okay, so the improvement is coming from like we discussed earlier, the strong convexity of this regularization that's quite natural for the probability simplex. That's saying that you can potentially work with an exponentially larger pool of selecting your stocks from compared to OGD. But still, like we're measuring the regret on the logarithmic scale. So having a regret of square root of t, so even though at the end of the day, on average, in every iteration, the growth rate would match more or less what the growth rate of what the growth rate of the best constant rebalancing strategy. But it's still a big loss, right? Comparing to what you could have gotten here. So the questions that we're going to be focusing on in today's lecture is really, can we do better in this problem? Can we do even better than these two regret bounds? In particular, like whether we can improve the dependence, improve the dependence on square root of t. So there's one example that we know where the OGD actually have logarithmic regret, right? So that happens that when Ft is strongly convex, when we know that we have a family of problems that where Ft is M strongly convex, so that says that with a perfectly chosen learning rate, then OGD has a regret. OGD has a regret of g square divided by m log of t. But is this loss function that we are is this ft of interest here minus log of rt transpose x? Is this strongly convex? This is clearly not the case, right? Because strongly convex requires a quadratic function to requires that there is a quadratic function to be a uniform lower bound of the function anywhere, right? But in this case, if you look at if you look at this function, so for those directions where x is in some sense orthogonal to RT, then we don't really have like any curvature in those directions, and everything stays flat, and that means that we couldn't possibly be any strongly convex with any parameter m that's larger than 0. Okay, so the answer is no. So then the question is, can we still do something better, and can we weaken the definition of strong convexity somehow such that it covers this is log loss that comes from the universal portfolio, and then hopefully we'll end up getting an improvement that's very similar to M strongly convex. So what is a special property of this loss that makes it potentially possible for us to improve the regret further? So that brings us to the notion of exponential concavity. Okay, so we say that a convex function f is alpha exponential concave if you take the exponential transformation of this function f, then it suddenly becomes a concave function. This is certainly the case for the log transformation, because if we take exponential and choose alpha to be 1, then we get the linear function, right? And that's concave. A linear function is both convex and concave. Okay, so a useful property or equivalent definition of exponential concavity that makes it more transparent is the following. So for all f such that f is twice differentiable, where we can talk about the Hessians. F being alpha exponential concave if and only if the Hessian of say at location X. So maybe this F is like we can talk about the local like exponential concavity, which as a slight generalization. So F is alpha exponential concave if and only if the Hessian of F can be lower bounded by alpha times the gradient transpose. This is something that's somewhat similar to strong convexity, right? Because recall in strong convexity, and for twice differentiable functions, then we have this property that you have m times identity. Instead of having identity here that covers all the directions, so alpha exponential concave only requires this Hessian matrix to have curvature in the direction that's specified by the gradient itself. Okay, so you should also maybe like you might be able to connect this on the extremely high level to the definition of self-concordance. So in self-concordance, you are bounding the second derivative, you're bounding the third derivative using the second derivative. So in this case, you are bounding the second, you're bounding the you're lower bounding the second derivative using first derivative. Okay, so to build more intuition, let's maybe verify that the equivalent property for equivalent definition for the log loss that we are considering. Okay. Okay, let's say that this is function f. Let's maybe calculate the gradient. So well, this is just minus r transpose tx of rt, right? So now let's calculate the Hessian by taking the gradient of every coordinate of this gradient. And then I guess by simple calculus, you get this, and then you get RT is a constant. You take the derivative of RT, multiply with whatever that's down here, which recovers to 0. And so you have 0, and then minus RT. And then you want to multiply the gradient of whatever that's down here, and then transpose that, you get RT transpose, and you end up getting RT transpose x square, which well is equal to the gradient transpose, right? Just to split a square into two pieces and then multiply this -1 in both pieces, and then you can recover this. So what this is saying is that, well, since this is equal sign, so that implies that the Hessian is larger than 1 times gradient transpose. 1 1 exponential concavity. Let's verify another example that to show that in some sense this is strictly weaker than strong convexity. So suppose function f is m strongly convex, and we wanted to show that this implies that this function is exponential concave with some parameter. Okay. Let's say m is strongly convex, and also in the domain in K, such that the gradient of f is small, always smaller than g. Okay, so this is saying that the function is m strongly convex, and in the restricted domain, this function is also g Lipschitz. So let's start with the gradient and gradient transpose. So I argue that you can on the semi-definite ordering, you can bound the gradient transpose by using the fact that of this G Lipschitz property with G square times identity. Okay, so this is a particular direction. This is saying that I'm bounding this particular direction using an isotropic matrix that has the largest value in all directions. Okay, and now, well, by the definition of M strong convexity, I can further use this identity to lower bound the Hessian matrix. This is coming from the G Lipschitz. And this holds for all x in K, okay, which says that M strongly convex implies F is G square over M, implies that implies that F is like you want to switch this G square over M to the other side so that you recover the definition of self-concordance. F satisfies the Hessian of F is lower bounded in semi-definite ordering with M over G square gradient F transpose. Okay, which says that this is m g square exponential concave. Yeah, there's another property of the exponentially concave functions that's very intuitive and that resembles of the result that we learned about strong convexity. You can think about this as a generalization that we will use in the analysis of the online Newton's method. So let me state that now before stating the algorithm. So I'll call this a useful property of exponential concave function. Yeah, if there are any part that's not clear, and if you're not following any steps, please let me know, and please stop me and ask the question right there. All right. So this is lemma 4.2 of the OCO book. Okay, so F satisfy alpha exponential concave, and the domain in the domain of K and G Lipschitz. Yeah, then for any xy in K, we can recover something that's similar to the first order definition of strong convexity. So this is saying that we're linearizing the function f at location y, and then compare it to the actual evaluation of the function at a different point x. So this equation will be true for an arbitrary convex function, but for functions that satisfy alpha exponential concave, then we can, in addition, add a trading term that looks like x minus y transpose gradient f of y transpose multiply with x minus y. This is terms is mu for exp concave functions. So what is gamma? For the gamma parameter to be equal to half of the minimum of alpha and 1/4 GD. Yeah, so I'll leave this as a useful property. The proof of this is super interesting. It's short, so I encourage you to read the details of this lemma from the OCO book. I'm not going to be covering it today, but instead I'll use this to derive online Newton's step and use it to derive the regret bounds for online Newton step. Okay, so the key intuition is that to try to find the analogy between this and the strong convexity. So recall that in the strong convexity, for any fixed xy, so this new term is half m multiplied with the norm of x minus y. Yeah, measured in the notion of strong convexity that you state there your function f satisfies. You have x minus y norm square, so that would be strongly convex. But in this case, you only require this inner product to be on the rank 1 kernel that's specified by the locations that you're taking the gradient over. Okay, so intuitively that should be the property of exponential concave function following the equivalent definition of exponential concavity. So let me I guess state the theorem and then just state the let me state the algorithm and of online Newton step and state the theorem before we go to our break and then come back for the analysis. So the algorithm takes in, as usual, convex feasible region, horizon T, some initial point, and well, two parameters, gamma and epsilon, that are non-zero, that are, I guess, positive. And well, we, in addition, specify this A matrix A0 to be epsilon identity. And in every iteration, the agent, so your algorithm, just play xt, and then you incur a loss of ft, xt as usual, and well, you update your at using at minus 1 plus I guess receives the feedback, receive feedback, the gradient of t, which is a gradient of ft at location xt. So again, notice that this is a full information setting, and then you basically add to this matrix with this rank 1 matrix that's given by gradient transpose. Okay, and once you have that, you do a Newton step to calculate the strategies that you're going to adopt in the next iteration. So it's a two-step procedure. So yt plus 1 is equal to xt minus 1 over gamma at inverse gradient t. Okay, so this should be familiar to you. So if at is chosen to be the Hessian, if you have access to second order information, if at is chosen to be the Hessian, then this would be simply the Newton's update. Okay, so this is calculating the Newton direction. But you do not actually observe the Hessian. Instead, this at is constructed sequentially by keep adding the gradient transpose to the matrix. So you can think about this as some kind of a quasi-Newton update. So technically, this is still a first order method because all the algorithm have access to are gradients. You never really have access to the second order information anywhere. On the other hand, well, this is not a Krylov space method. In the sense that the Nesterov has formalized a Krylov space method such that all the points that you play needs to be within the Krylov subspace, which is a span, which is in the linear span of all the gradients that you've observed so far. This is not it because there's this AT inverse, which creates a curvature that you can potentially play points that's outside the Krylov subspace. So this is somewhat subtle. It's a quasi-Newton method. It's not really second order. It's first order, but it's not the typical first order, which falls into the Krylov subspace methods. And 1 over gamma can be thought of as a learning rate. So in this case, like in the theorem, there is a fixed learning rate that one can choose in order to get a good regret bound. Okay, so this is not yet a complete update. So after getting yt plus 1 from the Newton update, this might make you infeasible, right? So this might get you out of the feasible region K. So you have to somehow project it back. And instead of simply projecting it back using the Euclidean geometry, now we project it back to the feasible region under the norm that's given by AT. Okay, so this is our mean of x inside K, and we want to minimize the yt plus 1 minus x measured in terms of AT norm, yeah, with or without the square. Okay, so that's algorithm. So in some sense, it's projected. It's not a Euclidean projection, but rather an oblique projection after taking a quasi-Newton step. Okay, so is this algorithm clear? All right, so so the main theorem that we're going to be talking about today is that when we choose gamma to be half minimum of this alpha parameter and 1 over 4 GD, and GD is a standard Lipschitz constant, the diameter of the space. If we do this, and then if we choose the epsilon parameter to be 1 over gamma square d square, and for all t larger than 4, you have a regret bound of t smaller than 5 times 1 over alpha plus gd n log t. Yeah, so notice that the key feature of this is this log, factor, which improves exponentially over all the previous methods that have square root of t in the regret bound. Although, like arguably comparing to say follow the regularized leader, like the dependence on n is not great. So you have a leading n here rather than a log n. Okay. But for now, I think it's more important to focus on how one can get the logarithmic dependence on t, and then just treat everything as constant. So we'll take a break and we'll resume at 2011, where we're going to talk about how do we make sense of this theorem and how do we prove this theorem using exponential concave analysis. All right, see you guys in a little bit. All right, let's resume the lecture. So, well, let's analyze the online Newton steps and then prove this regret bound. Let's break down the analysis into two parts. First, we're gonna prove this lemma that in some sense gives us a like instance dependent regret bound. So let's first prove this lemma, just following the proof that's presented in the Hassan textbook. So this is smaller than 4, 1 over alpha plus GD, the sum of T to T, gradient transpose AT inverse gradient transpose, plus 1. Yeah, this plus 1 is outside the summation. So we're only adding 1, not adding T here. Yeah, otherwise it doesn't make sense. Okay. So so the proof is pretty intricate and it relies on the property of exponential concavity. But on the other hand, you can also you can still see the structure that's inherited from all such proofs of first order methods. And specifically, since we want to bound the regret, so let's maybe start bounding every individual summand of the regret. Okay, so by the useful property of exponential concavity. So notice that this is something that resembles strong convexity. So suppose you replace exponential concavity with strong convexities, you'll end up getting the same type of arguments. So by this, you can lower bound. So any comparator u or x star with a linearized version of this function at xt plus gradient t at xt. So this will be the following the convexity of function ft. But then now that we have exponential concavity, we can, in addition, add this additional improvement. Wait. Yeah. Gradient T transpose x transpose minus xt. Right? And if we move things around, and then we get the regret bound for this term for the time t against x star. So you will by simply moving everything to the left hand side and then switch the sign, we'll get t xt minus x star minus half gamma x transpose minus xt transpose gradient t transpose x star minus xt. Okay, so this is something that we're gonna keep. So notice that comparing to the reduction in the general convex case, now we have this additional term that can potentially give us quite a bit of benefits to make to lower the total regret. Now by the update rule of I guess Newton's method, xt plus 1 is equal to ik at of xt minus 1 over gamma at inverse gradient t. using this update rule. So then let's follow the kind of standard arguments that we had for analyzing the convergence of gradient-based methods, but let's measure that in a different geometry, right? To somehow construct this telescoping substructure. So in the standard analysis, we will start with xt plus 1 minus x star, square, right? And then we expand this whole square and make them the two quadratic term and then the cross term in between, so that we can somehow make use of the update rule and then construct a telescoping structure. But here, instead of using Euclidean norm, let's make use of this AT norm that was actually being used in the update. Okay, so notice that the projection is based on this AT norm. Therefore, by the non-expandedness of the projection, we can bound this with the possibly infeasible points that's before the projection. So this trick suffices, and that allows us to deal with the constraints and deal with the projection step. And well, now that we have something that we can get rid of this nonlinear projection term, and we can write this as xt minus 1 over gamma at inverse that minus x star in at norm. Okay, let's decompose it to construct the telescoping structure at. Yep, notice that this depends on t, so it's not really a telescoping structure because they won't cancel out as easily. But we'll see that this leads to interesting observations that we can leverage upon by simply just replicating the same arguments. So let's first write out the AT inverse measured in a t norm square. And then finally there's this cross term that takes the inner product between xt minus x star with the gradient. So thanks to this quadratic form, so we still have this at in the middle. Then there's at inverse gradient t. Okay, so luckily these two got canceled out. Okay, so so this is saying that now we get an upper bound of this term, which appeared. We get an upper bound of this term, which appeared in the in the regret bound. Which there appeared in the regret upper bound. Right, so suppose we move this to the left-hand side, then we get something that we can substitute into star. Okay, so let's start a new page. So by just move it around, we get half gamma xt minus x star transpose theta t smaller than 1 over gamma square at inverse gradient at square and minus xt plus 1 minus x star at square. Okay, and I guess further apply gamma over 2 on both sides. let's get rid of the constant, and sum over t from 1 to t. So even though it doesn't really telescope due to this different norms, we can still try to add things up to see what happens. Okay, so let's multiply this gamma over 2 on both sides and then try adding things up. So on the left-hand side, we have the sum of t from 1 to t, xt minus x star transpose gradient t. And on the right-hand side, multiplying gamma over 2, so we get 2 gamma, 1 over 2 gamma. And notice that this term, so you have this AT inverse that's here. So it's like it cancels out with this AT in the middle. So you have AT inverse, and you have AT inverse, gradient T transpose. So just pick any two that cancels out. Let's pick this two that cancels out. Then it gives us the norm of gradient T on the AT inverse norm, right? Square. So let's stick to that notation so that we don't have to keep rewriting this AT inverse. And now that we're summing over everything, we have this sum over t. Now so for this sequences of sum, let's try grouping together all those. Let's try grouping together all those that have the same index on x. So starting with the first one. So for the first one, we don't have anything that cancels that aims at canceling it out with. So we'll keep it. We get x1 minus x star a1 square. But starting from the second one, you can cancel out with the next iteration. So we have the sum of from t from 2 all the way to t, and then we all have things that cancels out with everything that we have, which gives rise to say xt minus x star. So at time t you have something that's negative, so that gives at and at plus 1 minus at xt x star. Okay, can people follow this step? And once we have that, there's one last term that we do not actually wait. You have this, you have at plus 1, so we are starting from, okay, so this is t starting from 2, which means that we have 2 minus 1. So yeah, sorry, I think the index should be at, and then minus at minus 1. Okay, so once we have this, in the last iterate, we still have like one last trading term, which is half gamma. Okay, I'm missing the half gamma everywhere. So we have the half gamma x t plus 1 minus x star with a t squared. Okay, so notice that this difference is actually quite convenient, right? So with this difference, we can apply the fact that that we're updating at using at minus 1 plus gradient transpose. This is how we are constructing this, and now it comes up the difference between the two, which means that we can simplify this is quite a bit. Okay, so if we do that, we get sum of t inverse transpose plus half. T minus x star okay, and there's a last term that's obviously negative, so I'm just gonna replace that with with 0, and then makes this an inequality, okay? And also dropping the negative. Okay, I hope you guys are able to follow it so far. So it remains to actually just plug in this inequality into this equation star that we had in the previous page. So let's look at what it is. Okay, so let's try to plug in this. Plug in the summation of this star equation over t, and then we are bounding the first term, and then we'll keep the second term where it is. Okay, so plug into this, we get the sum of ft xt minus ft x star sum over t. And this is smaller than, we're just replacing this equation above. 1/2 gamma, sum of the gradient, t measured in AT inverse norm square. We'll add this singleton term, A1 square here. And then we'll have this t from 2 to t, x t minus x star gradient t transpose xt minus x star. But then there's something else that's trailing that's coming from the exponential concavity, right? So this is the thing that's coming from exponential concavity that's gonna help us quite a bit here. Notice that we are just adding these things up over t. So we'll get minus sum of t from 1 to t, xt minus x star, t transpose xt minus x star. Yeah, so I think I just missed the gamma over 2 thing again. So gamma over 2 coefficients. So these two actually canceled out except for the first term, right? So let's cancel out everything that starts with t equals to 2, and we get plus. So maybe let's rewrite this. Okay, write this in A1, x1 minus x star. And everything cancels out except the last term, which is something that's negative, which gives us half gamma, x1 minus x star transpose gradient t transpose x1 minus x star here. And now these two terms are something we can combine. And this is really the most critical step because everything cancels out and it makes use of the property of exponential concavity. And that gives us 1/2 gamma of gamma. It's 1 minus x star transpose A1 minus Okay, so notice that A1 is equal to epsilon identity plus gradient 1 transpose. So the difference of these two will gives us an identity matrix, which means that we get simply 1/2 gamma gradient versus square plus um, 2 gamma guess epsilon multiply with x1 minus x star square Euclidean norm, and this term, this is smaller than 2 gamma epsilon d square. And we'll substitute in the definition of epsilon when the choice of epsilon is equal to 1/gamma square d square, right? 1/gamma square d square. So this gives us just I guess 1/2 gamma. Right? So now you have 1/2 gamma here on the second term, and combine that with everything that's in front, then you get 1/2 gamma sum over t gradient t at inverse 2 plus 1. Okay, and then again, finally, you substitute the choice of gamma to be equal to half the minimum of alpha and 1/4 GD. Okay, since you have this, then we can just replace gamma, replace 1/gamma with the sum of these two things, and then finally, so I'm a bit out of space, so let me draw a long arrow because I don't want to move to the next page just for this. This is smaller than 8 times 1/alpha plus GD by simply using the fact that gamma is a minimum of these two. Then we can replace 1/gamma with an upper bound that looks like this, multiply with plus 1, as expected. Okay, so this concludes the proof of this key lemma. Okay, this is key lemma that looks like the following. Yeah, I think this should be 4 rather than constant should be 4 rather than 8 because we have 2 in a denominator. Okay, so finally, it remains for us to make use of this lemma to construct an upper bound of the final regrets for online Newton step. So let's write what we've proven so far. We've got the sum of ft xt minus ft x star. We've shown that this is smaller than 4 times 1/alpha plus gd. Okay, so in order to continue, it remains to substantiate this with an upper bound. Bound this. So the proof of the main theorem will be devoted to bounding this term. Okay, so this is if we expand it, and notice that this is a scalar, right? So for the scalar, we can simply add trace to that, and using the property of the trace, we can like wrap around the matrix multiplication to the other side. So we can make this the trace of AT inverse gradient T transpose. So now this is Rn by n, and this is also a matrix Rn by n. And notice that this is equal to, like, sometimes you can use the notation of the matrix inner product, which essentially makes use of the take every coordinates, takes a product, and then add everything up, right? So you can write it in this format. And since all these are symmetric matrices, so I'm not being careful about the transpose, but yeah, you can essentially write it either in trace or in this inner product form. Yeah, I personally find this trace form more intuitive. Okay, so now notice that this gradient T transpose is the difference between it's the difference between AT and AT minus 1. So let's substitute that into here. So we get trace of AT inverse AT minus 1. Okay, now we have the AT that cancels out. We have the trace of identity minus AT inverse AT minus 1. So why can we do the inverse always? Since we're starting with A0, that's an identity matrix with a leading coefficient of epsilon. So AT is always strictly positive definite. So it's non-singular, and there's a unique inverse, right? So we can always write AT inverse without worrying too much. The trace, let's use the definition of the trace to be the sum of the diagonal elements. And since it's the sum of the diagonal diagonal element is also the sum of the corresponding eigenvalue. Okay, so this will be the sum of I of 1 plus the okay, so actually, like, I'm abusing the notation a little bit because this is not a symmetric matrix. So what this really means is that this is the square root of the eigenvalue of the symmetric matrix, matrix that uses this transpose of that. So we can construct this. I can construct this eigenvalue as a scalar, and then this trace will be taking over the sum of all the eigenvalues of that symmetric matrix instead. So and then if we use the inequality with respect to log, epsilon smaller than log 1 minus 1 minus epsilon. So we can replace this with sum of I from 1 to n log by take epsilon to be wait, this is minus Okay, so I'm taking this epsilon to be 1 minus lambda I inverse A t minus 1. Okay, so if we take this and apply this, then we can upper bound each segment of this sum with a log. So we get log I guess lambda I inverse a t inverse a t minus 1. Okay, and now let's push this summation inside. So we get log of the product and 1 to I to n. So we get the lambda inverse at minus 1. Okay, so that actually gives us a determinant. That gives us a determinant of the matrix at inverse at minus 1 inverse. That gives us a determinant of this matrix. And by the property of the determinant, which is the same of the product of the eigenvalues, we get this to be equal to log of at over at minus 1 determinant. Okay, so by the property of log, let's make this ratio a difference. So we get log determinant of at and log determinant of at minus 1. Now this becomes something that will cancel out. Supposedly sum everything over t. So that's exactly what we'll be doing. So add up t from 1 to t. We get the sum of t from 1 to t. T inverse square to be log of a t determinant minus log of a0 determinant. Yeah, but what is a0? A0 is epsilon identity. So a0's determinant is equal to e to the power of n. So recall that the determinant is the product of the eigenvalues, and the determinant is yeah, you can calculate the determinant for an arbitrary matrix, but you can also diagonalize it and just multiply the eigenvalues, and this well, this one's is equal to the sum of the gradient transpose from 1 to n plus a0, which is epsilon times identity. Okay, so using the fact that the gradient is the function ft is g Lipschitz, we can upper bound this at in semi-definite ordering with wait, so this is a sum from t1 to t, not to n. So then we can upper bound this with t times g square plus epsilon times identity, right? So now let's take determinant of this. So since this is dominated by this identity, then we can upper bound the determinant of at to be the determinant of this matrix that dominates at, which will simply gives us which will simply give us tg squared plus epsilon to the power of n. Okay, which means that the final bound here would involve simply taking the log here we'll get n times log of t g squared plus epsilon minus n log epsilon. Then it remains to simply substitute in the what epsilon is. So we know that the epsilon is 1 over gamma squared d, and we also know that the gamma is half mean of alpha and 1 over 4 gd. So let's first substitute epsilon, then we get n log tg squared plus 1 over gamma squared d. Okay. Maybe let's first combine these two. Since we have this subtract, let's combine these two by making this divided by epsilon. So you get epsilon here, and then we get epsilon plus 1. Okay. Yeah. Now let's substitute this epsilon equals to 1 over gamma square d square. We get n log gamma square t g square d square plus 1. Okay, now let's substitute gamma and use the second leg of this minimum. Since we know gamma is smaller than 1 over 8 times gd, then we can write this to be n log. Since log is monotone, you can write this with 1 over we get 1 over 64 t, and then all this g will cancel out with a g squared d squared and g squared d squared plus 1. Okay, and that gives us a final bound on the order of n times log of t, right? For t larger than 4. So you need t to be slightly larger to handle the trivial case when t is equal to 1. And yeah, I'm not too sure why they choose a specific number t greater than 4, but apparently t equals to 4 works. And this completes the proof for the main theorem. Okay, let's take a step back and look at the structure of this analysis. So we start off proving this regret that's data dependent, and the analysis is, although it's somewhat intricate, it's still very similar to the kind of analysis that we use to prove the convergence of the gradient descent in the third lecture. Right, so we make use of convexity. So when we have exponential concavity, we make use of the stronger version of the convexity of first order condition under alpha exponential concavity. And then we try to construct the telescoping sum, so things cancel out. So things gets quite a bit ugly over here, since now we have a inner product that's different in every iteration. But thankfully, we're constructing this AT by keep adding the gradient transpose there. And that's connects to this additional benefits that's given to us by the alpha exponential concavity very nicely. So it ends up canceling out, right? So they end up canceling out here. Okay, so once we have this, then it remains for us to simply bound every term and then bound the gradient in terms of this AT inverse norm, and that turns out to be a straightforward calculation that involves nothing but tedious algebra. And then there's this trick that replaces the trace and inner product with a logarithmic factor, so that we can create this telescoping sum structure. So that's kind of cute. But once you have that, everything else becomes a simple calculation that construct the logarithmic regret bound in the end. Okay. So so the last thing that I wanted to say about this online Newton method is that what kind of computational complexities that it requires in every iteration, and what's the space and time complexity of this algorithm comparing to OGD. Computational complexity. In every iteration, the online Newton methods needs to solve this problem of finding the Newton update, right? So that involves AT inverse gradient T. So solving this linear system of equation naively requires order n cube computation, right? There's actually a trick that you can get away with spending on the n square using Sherman Morrison. Sometimes called the Sherman Morrison Woodbury identity, or matrix inversion lemma. Okay, that allows you to calculate this AT inverse incrementally when every rank 1 update is added to this. So what this lemma says in this special case is that for any rank 1 perturbation of this matrix A, and if you calculate its inverse, it can be decomposed into the inverse of the previous iteration minus something that's more easily calculated. More easily calculated using this. Okay, so notice that this is something that you already have from the previous iteration, and this x is just a gradient, and in fact you also have this Newton step in every iteration. Okay, so these are the Newton step from previous iteration. So using this Sherman Morrison Woodbury identity, you can reduce the time complexity from O(n) cubed to order n square, since the computation only involves multiplying with this matrix A and A inverse, which is of size n square. Right? The space complexity is n square. So the other step that's needed for running the online Newton step is this projection step, which has a form of minimize yt plus 1 minus x measured in terms of a t norm subject to x is in this convex set K, right? So the convex set K is a probability simplex. Therefore, like solving this, you can run projected gradient descent. You can run other methods. You can run interior point method. You can run any methods that we learned from the convex optimization part of the lecture. And then the best algorithm will have a complexity that's proportional to order n square. Maybe if it has linear convergence, then it's order n square times log 1 over epsilon, something like that. So overall, so every iteration of online Newton methods takes roughly O tilde n square time complexity and O n square like space complexity. So this is a lot more, still a lot more comparing to the online gradient descent, which requires only O(n) space and time. Okay, And in terms of the regret bound, like we said, that it improves in terms of the dependence on t exponentially from a square root of t to log t. But the dependence on a, dependence on this n parameter, which is the number of stocks that you are trading using this universal portfolio algorithm, has actually become worse. So now it depends linearly in n. So that's something that you could potentially improve. Suppose you combine the idea of online Newton update with entropy regularization. Okay, so that's something that we won't be able to talk about. But overall, so that concludes the main part of the entire course of the 16th lecture. So in the remaining 3 lectures for this course, so we'll be going through some of the more advanced topics. So none of those topics will be covered in the homework 4. So at this point, you have already learned everything that I have to teach that's testable in the homework. Okay, so I hope you find like this part of the lecture online convex optimization and its connection to first order and second order optimization in the standard convex optimization setting interesting. And hopefully this will help you and you'll end up using these techniques somewhere in your PhD study. All right, yeah, thank you guys very much. Yeah, go do the homework and you'll learn a lot more. And the lecture video and all my handwritten notes will be posted on the course website and on Piazza by the end of the day. Thank you all.